So today was homework 3. It is long. It is challenging in parts. This homework 4 and homework 9 is as hard as this course is going to get. There is going to be no moment in the course any harder than this homework, the next one, or the ninth one. And it'll be a matter of personal taste which ones you found most unpleasant. Given that I've seen almost all of you did very well. You seem to have survived it extremely well. So there'll be some moments that are, I'm sure, tricky that not everyone got perfectly the first time, but this is it. This is the apex pretty much of the course difficulty. And hopefully things will just continue to become smoother sailing as we go along. This is next week. Starting with problem 1 is Michelle.
Good morning.
Good morning.
All right, I'm a little bit out of it, so let's see.
Oh, I let you share. Oh my God. Wow, I remembered finally. Okay, sorry.
So problem 1 is in a population of N diploid individuals undergoing Wright-Fisher sampling. P naught is the frequency of the A1 allele in the current generation. P1 is the frequency of A1 in the next generation. So what is the probability that P1 equals X for values of X between 0 and 1? So basically, we're looking at a binomial distribution. And you went over this on Thursday, and I still don't really understand why. But so you can rearrange your p-value to be your count of an allele, which has this relationship here. So
all right. Yeah, no, this is all correct. But you're confused about why it's correct.
Yes, I'm confused about why it's correct. So once you do that, you can sort of plug in the probability that your count is 2nx is 2n choose 2nx times p naught to 2nx 1 minus p naught to the 2nx minus 2nx. And then that is essentially the same as the probability of p1 equals x. But so when I just did this before I had hints, I was like, I had like 2n choose x or something like that. So I don't understand why.
Yeah. Okay. So let me see if I can figure out how to share my screen. That's okay. And of course, okay, there we go. So this is just exactly what you had, but we're going to talk through it a little bit. So the idea is the number of A1 alleles is binomially distributed. It is a binomial random variable. So the number of A1 alleles next generation will look very much like, I probably should have written this all the way out in a different step. But the probability that there are A1 alleles next generation is just that the probability that A1 is, say, I, is 2n choose I, p to the I, 1 minus p to the n minus I. That's all clear to you? That the number of alleles is binomially distributed, right?
Yes.
Yeah. So So we have this random variable a, little a, we'll call it, that is binomially distributed, and with so that with p0 and 2n draws. And then we create this new random variable, we'll call it pi, that is nothing more than ai divided by 2n. This new random variable changes the observable outcomes. It doesn't change any of the probabilities, right? So if the probability ai equals k is something, and pi is equal to ai divided by a constant, the probability pi equals that same thing must be the same as the probability ai, isn't it? Think of this like so the intuition some students liked was, imagine a Bernoulli random variable with two outcomes, 0 and 1. And then divide those numbers 0 and 1 by 1,000. Your outcomes are now 1 in 1,000 and 0, but the probability of those outcomes hasn't changed. So the only thing that is changing is the probability that a1 equals, say, I would be 2n choose I, p0 to the I, 1 minus p0 to the 2n minus I. But if you set x equal to I over 2n, well, then the probability of the outcome measures are changing, the probability measures are not. So this is still just a binomial random variable where the outcome isn't an I, it is an I times 2n. That is only vaguely helping you, I'm guessing, from the face you're making.
I'm processing it.
I probably should have done this out in another few steps. That probably would have helped. Did anyone do this in a number of steps to show out what I was talking about nicely? No one wants to volunteer there. They're neat little. I should have left this as A's first.
I have a question.
Yeah.
Maybe to help clarify it, I'm not sure. So you mentioned that A1, the frequency of A1.
A1 is a count, yes.
So the count, you mentioned that was binomial?
Yes. So the count of A1 alleles, which I'm going to call little a1, is binomial. So the probability little a1 equals I, for some value of I, is 2n choose I, p to the I, 1 minus
Gotcha.
p to the 2n minus I. You're probably happy with that. And then if you make a new random variable that isn't a1, but is p1, and p1 is defined as a1 divided by a constant, the probability p1 is equal to this is equal to a1 over 2n is exactly the probability that a1 equals 2n times that number. The probabilities haven't changed. The outcome measures are divided by some constant. So if you flip a coin, the probability of getting a heads or a tails is still a half. But if you divide the value of a head by 1,000 or divide the value of a tail by 1,000, you'll have a probability of getting whatever you had for a head before, maybe a 1 over 1,000. And the value of getting a tail is now 1 over 1,000. But the probabilities of those observations are still a half. You're changing how you're measuring the outcome. You're not changing any of the probabilities. When A1 is equal to I, P1 equals I over 2n. When P1 equals K over 2n, A1 equals K.
This might be kind of a crude way to think about it, but is it kind of like kind of like the same way we think about like a unit conversion where you're not really changing.
It's not a crude way. It isn't the exact way to think about it.
Okay.
All you've done is made a unit conversion. You haven't changed any of the probabilities. You haven't changed the probability of landing anywhere on the line. You've changed the label of the line. So if some little section corresponds to the probability x equals that value, and you change the label of the line so that it's now labeled in units of y, the probability of ending up in that same tranche is exactly the same. Although the unit value of that tranche has now gone from x to y. That is the exact way to think about it. So the outcomes differ because we've transformed the variables, but for this corresponding transformation of variable, the probabilities are the same. Does that make sense to everybody? Or at least makes as much sense as it's going to right this second. And this one might be useful to plug in some values for, just like maybe open up Excel, plug in some values of like, make a population of size 20 and see what the probability of next generation there being 1 allele, 2 alleles down to 40. And see what values that corresponds to the next generation's allele frequency being, and so forth. Questions about this so far? Okay, let me stop sharing my screen. And Carmen, do you want to take a shot at number 2?
Yeah. Okay, so I was kind of in the same boat as Michelle on this one, but I think I understand it now. So you use the same logic for this question as the last question, replacing the count with the probability.
This is absolutely perfect, right? You have a variable P1, and that's got some expectation. And you know that expectation is equal to some other random variable A1 divided by 2n. You pull the 2n out of the expectation. And you know the expectation of a binomial random variable is 2n over P0. You divide it and you got P0. Couldn't be any better. You do the exact same thing with the variance. We're looking for the variance of some random variable P1, which is equal to A1 over 2n. You pulled out the 2n in your head and remembered to square it. And that was brilliant. And then you said the variance of P was 2n times P0 times 1 minus P0. Fabulous. Cancel some stuff. Great. Absolutely perfect. And this is the easy way to get the answer. You could have, of course, written down a summation and added those values and done it from first principles. But the way things are defined, P is just A over 2n. And you know how to get the moments by pulling the constants out. Does that make sense to everyone? And so this is the intuition, right? When we're binomial sampling, when we're looking at the counts, the expected count next generation is going to equal the current count. Therefore, the expected frequency next generation is going to be the current frequency. The variance in the count next generation looks like the sample size, 2n times PQ. But the variance in the allele frequency is much, much smaller. It's PQ divided by 2n. Because when you take a random variable and you divide it by a constant, the variance goes down by that thing squared. So we end up with PQ over 2n, sort of much smaller sort of variance. Everybody clear on this? Makes sense? And for the rest of the term, we'll be thinking about allele counts, allele frequencies, mostly frequencies. We'll mostly keep ourselves in the frequency space. But we will know that we got to the frequency space because we started out with a binomial randomly generated number and then just divided by a constant. Because we're going to assume population size is constant most of the time.
Can I ask
Yep.
really quickly, just a reminder why when solving for the variance, why we square the denominator?
Well, you pulled out so remember that take a random variable x,
Mhm.
multiply it by a constant. The variance of that new random variable, which was x times a constant, is equal to the constant squared
Okay.
variance of x.
Okay.
So if you have divided by 2n, when you pull it out, it becomes a divided by 4n squared. All sensible? And yes, this is the most common error you will make in the course of the course. Forgetting when you pull out a constant in front of a variance, it comes out like a square rather than a scalar. You'll see this over and over again. Other questions? Okay, Sebastian, problem 3.
Okay, let me share my screen. So, well, what I did is that I just multiplied the probability we had for the first bit with the probability of this value, and that was my approach to this bit. I don't know if I got it right.
You're getting there. You're almost there.
Yeah, I thought I was wrong when I didn't see like a long summation. I was like too tired to keep trying.
It's okay. So this is the probability that P1 equals X. So we can think of this as the probability P1 equals X. And so what we would want here is the probability that P2 equals, say, 2ny, as given that P1 equals X, summed over all the possible values of X. So let me see if my solution is sufficiently clear. So look at 3. So you guys can see my screen?
Yep.
We're going to start asking, what is the probability that P2 equals some value y? And we're going to assume that we know for the moment that P1 equals X. So the probability P2 is y is just is just a binomial probability where we assume P1 is X. So it's 2n choose account 2ny times x to the 2ny, 1 minus x to the I don't know, that's 2n minus 2ny. I've written it sort of in a very funny way. But the issue is we don't know that P1 is X. If we knew P1 was X, we'd be all done. So instead, to find the value, the probability that I should have said P2 equals y, or I guess boy, this was not a beautiful way. I'm sorry. I'm trying to teach you the total law of probability. So the total law of probability, I've got a random variable y, and I want to know the probability y is equal to yj. That's equal to the probability that y equals yj, given some other random variable, x, is equal to x1 times the probability that x does equal x1 summed over all possible values of x. So this is more or less Bayes' theorem writ large, that the probability that y is some value is equal to the probability it is that value given some other random variable times the probability of that random variable summed over all possibilities. So the probability that y2 is y is equal to the sum over all possible values of x of the probability that P2 equals y, which is this, times the probability that P1 equals xi, which is that, summed over all possible values of xi. So this is simply n, 2n choose I, p0 to the I, 1 minus p0 to the 2n I, summed over all values of 2n, times 2n choose this thing. I over 2n is now the value of p1, goes there. 1 minus p, it goes there, goes there. We've just plugged in here. And then I've just rearranged terms, and that's it.
Can you explain a little more about why you plug in I over 2n to get all possible values of
So I
X
made the
and Y?
sum go from 0 to 2n rather than the sum, so recall that if P1 equals X, that is where now X is, so that'll be the same probability as A1 equal I if X equals I over 2n. If we define this is a count, this is the number of A1 alleles. It's 2n, choose the number of A1 alleles, the probability of picking an A1 allele times the number of A1 alleles, 1 minus p times the probability times the number of A2 raised to the number of A2 alleles. The probabilities are all in counts. 2n, choose the count of A1 alleles, the probability of picking an A1 allele, the probability of picking an A2 allele, the count of A2 alleles. So you have here, so the allele counts have to be between 0 and 2n. This is P0 is the probability of picking an A1 allele. I here is the count of A1 alleles, probably picking an A2 allele, count of A2 alleles. 2n choose I, P0. The probabilities haven't changed, just the whether the random variable is equal to an I or a 2n over I. Are you with me?
I think so. Getting there.
Getting there. This one's a little bit tricky, but we're doing it for one purpose and one purpose only. And that purpose is to get to problem 4. Does anyone have any more questions about this problem? Because problem 4 is the reason for all of this mess. Okay, up next with problem 4 is Christopher. You want to show how you set it up?
Yeah, I'm pretty sure I didn't get very far with it. So
You didn't get home on it? Okay, show us where you started, and then we'll.
yeah. Oh, oops. Are you guys seeing it now? Is that
So you had a probability in problem 3 that is not correct, but interesting. Okay.
Yeah.
Okay. And
So
you
after, using that incorrect formula, I tried to play. I was trying to do this summation thing because I know that was a hint that you had given. That's
so
as far as I got.
no, this is great. So we have a value for the probability of P2 equaling Y that is not correct, but it is there. Well, let's pretend for the moment it were correct. And then we're going to try to find the expectation of P2, which should be this probability times the value of P2 summed over all possible values of P2. So, so this is getting there. This looks like the probability, but I don't see like I got a P2 in here anywhere. So, so there should probably be a I over 2n value here, which would be the value of P2. This is your probability. And were this a probability, that sum would equal 1. But what you want is, oh, and that P should have been your P0. It's a little bit confused. Okay.
Yeah. A lot of it confused.
A lot of confused. That's okay. Does anyone want to show show off how they did this algebra?
Yeah, sure, because I just figured it out a few minutes ago.
Right.
So you set up the problem because the probability is the summation of x times px. So j is, oh, so right here I'm counting the expected value of a2, not p2. And so a2 can take on values from 0 to 2n, and then times the probability of a2 equals j. So this long thing is the probability of a2 equals j. And then you would change the order of summation by taking this summation out to the front because because everything involving I is encompassed in this long term. And then you would put this summation sign back into here, and this will give us the expected value of a binomial random variable, because this is the equation that we have for a binomial random variable having 2n trials, and the probability is I over 2n. So I over 2n is P1. And the expected value would be 2n times P1. And we would have I here, and you put I back into the front, you will have another binomial random variable having 2n trials and P0 as the probability of success. And so using the equation again, you will get 2n P0. And then you divide by 2n to get that the expected value of P2 is also P0. So by the same token, for all the future generations, it's going to be P0.
That's exactly perfect. The only thing you've done up in these steps is you started out with the exact perfect definition. You plugged in the correct equation for the probability A2 was J. And then all you used is the fact that multiplication, we can change the order of operations. And you've changed the order of operations and been able to pull out all of these terms involving I. And we have a summation of things only involving J. That is the definition of a binomial. Expectation. So you replaced it with the expectation of the appropriate binomial. And then lo and behold, you have another sum that is also the expectation of the binomial. Brilliant. Absolutely perfect. And there is no other easy way of getting to that solution. But we've gotten to say, let me show my screen for a second. But we've gotten to a really, really kind of powerful result. That is The expected value of the allele frequency from Fisher-Wright sampling doesn't change from one generation to another. So we will very soon be using the words to describe this kind of sampling as genetic drift. Genetic drift does not change the expected allele frequency. It creates a wide distribution of possible allele frequencies. And we can write down expressions for the mean and variance of that distribution. We see the distribution itself can get intensely ugly. We may have no good closed form expression for the distribution, unless we go to some weird matrix notation. It's going to be very hard for us to see what that distribution is right away, but we know what its first moment is. We know what the average is. In the averages, genetic drift does nothing on average to allele frequencies. Sometimes they go up, sometimes they go down. On average, they stay completely still. Genetic drift has no average effect. It has a variance effect. It changes the probability, the frequency of something, and it might in fact sort of widen the variance on the allele frequency, but it has no mean effect. On average, you stay at the frequency you're at forever. In practice, sometimes you go up, sometimes you go down, and it bounces around. But on average, it stays constant. That's what genetic drift is. That's what Fisher-Wright sampling is. This is nothing more than a sort of flat average martingale process, if that word means anything to you. Do we have questions about this? So this is going to be our intuition for the rest of our lives. Nothing about genetic drift changes the average frequency. So if you got a population, sample it, on average, the allele frequency is the same. In practice, it'll be different from the sampling, but on average, it's the same. Go through a bottleneck. Allele frequencies stay, on average, the same. Expand the population. On average, they stay the same, unless there's some selection going on. And we'll talk later about what selection is. But drift, binomial sampling from one generation to the next, doesn't do anything to allele frequencies on average. Their variance, it does affect. And we will use the fact that the average frequency of an allele doesn't change a bit under genetic drift to even derive some really sort of fun results by the end of this homework. Do we have questions about this so far? Does all make sense? And this is certainly one of those take-home messages you should remember, you know, for your career as a biologist, if you were heading into that field, that genetic drift doesn't change allele frequencies on average. In practice, it does if they go up or down due to sampling, but it has no average effect. Cool. All right. We're up to problem 5 with Shengji. Oh, I gotta stop sharing.
Okay, I think everyone is looking at my problem 5. So problem 5 is defining everything as in problem 1 with P0 equals 1 over 2n. What is the probability that P1 is greater than 0? So I'm using something else as my interesting. Okay, it's showing up. Okay, so I'm using this thing known as Google. What is this thing? Google Jamboard, basically a virtual whiteboard. Okay, so the probability that P1 will be greater than 0 is 1 minus the probability that P1 equals 0. And we know that the probability that P1 equals 0 is given by this expression involving the binomial, using the binomial theorem. And so if you just evaluate this expression, this will become 1 minus 1 over 2n raised to the 2n. And so the probability that P1 is greater than 0 is just 1 minus 1 over 2n raised to the 2n.
Perfect. You know for what?
Okay.
Does anybody have any questions about this? Couldn't be more straightforward. All right. Marissa, the next problem. Are you with us? No. Kiana, are you with us?
Yes, I am. So problem 7 then?
Yeah, I think so.
Or problem 6 actually.
That should have been 6, yeah.
Okay, let me share my screen. Okay, so we know that the probability that P1 is 0, or that the frequency will be 0 and after one generation is this term, because we found that in the previous problem when we did 1 minus it. And so taking the limit of this as 2n goes to infinity was just some math. We know from the textbook appendix that the limit as epsilon goes to 0 of 1 plus epsilon x to the 1 over epsilon is e to the x. And so rather than having epsilon to 0, what we want is a constant to infinity. And so if you set n to be 1 over epsilon, then you can do the limit as n goes to infinity. And so you have a limit as n goes to infinity of 1 plus x over n e to the n, which is e to the x. And that was just swapping n for 1 over e so that I could have the limit be to infinity instead of to 0. So now plugging everything back in, essentially our x, or how did I do this exactly? I believe I just plugged numbers in. To get this minus sign, I think I set x to be -1. And so if you do that, then you get e to the -1, which is 1 over e, which is this. So about 37% of the population leaves no descendants each generation.
Your first line there clearly convinces you the sign should be negative.
Oh, where?
Your probability P1 equals 0 is 1 minus, and then you wrote to me a limit as a 1 plus. So that's where your minus sign came from.
Oh, well, this is correct, right? I just set x to be -1. Okay, yeah, so going from this limit as n goes to 1 over epsilon line to this limit as 2n goes to infinity, for us, we just have x as -1, and that's where you have this minus sign in the center instead of a plus.
Yep, absolutely correct.
Okay.
To show you where that little approximation came from, you can actually derive it yourself relatively easily. So we start with 1 minus 1 over 2n to the 2n. And then I did nothing but raise that expression. I take the log of this expression, log base e, and then raise it e to that. So I've done absolutely nothing so far. That's e to the log of that. And then I do nothing again. When you have an expression involving e, when you put an exponent in there, it comes down as a multiple. So this is e to the 2n times the log of 1 minus 2n. And here I've simply used the Taylor expansion of a natural log, where I think we talked about this last time, the log of 1 plus x is really very, very close to x for any small value of x. So this is now e to the -2, this is what we had the line before. This is 1 plus a tiny little value x. So that's e to the 2n, and there we go, the exact same answer. All make sense? Sort of, that's where that approximation came from.
Would it make sense? I didn't get all the way through it. I was trying to think about it in terms of, this is almost like a Poisson situation, right? Where you have a lot
Oh,
of,
it most certainly is like a Poisson situation.
yeah. Could you use the formula for that as well in the way, or
How would you convert this in your mind to a Poisson process?
that's where I got stuck.
So let's imagine for the moment that that Fisher-Wright sampling were approximatable as a Poisson, where every n individual leaves 2 kids as a leaves leaves 1 kid. Let's that you reproduce yourself exactly in a Poisson, so that you leave exactly 1 child behind, so that the mean of the process is 1, and so what we have is now a Poisson distributed random variable, and we're looking for the probability that it equals 0 for something with a mean of 1. That would be e to the minus mean, which is 1, e to the minus 1, 1 raised to the 0 power, which is 1, over 0 factorial, which is 1. And you would get e to the minus 1. So, at least for the probability that you have no descendants, Fisher-Wright sampling may be reasonably well approximated as a Poisson process, at least at that end. At the other end, it might be a little funnier. The chances that you have like 2n descendants or just lots of descendants may not be quite right. And the variance of the numbers are going to be slightly off too. But this level of approximation is almost exactly equivalent to assuming the number of descendants is Poisson distributed with mean. And so by the way, that number is a third. Well, it's not quite a third. It's 0.36, whatever. And that's another thing to have in your mind. You got an allele, and then you do nothing more than genetic drift. You just sample, Hardy-Weinberg sample next generation. 37% chance that allele got lost. So only from drift. So as a geneticist, as maybe a human geneticist here, your first thought is, if someone has a new mutation, it's a 37% chance it's gone the next generation. The vast majority of rare new things, are lost very rapidly. A third of them go in the first generation. Many of them go in the generation after that, or the generation after that. Most variation does not last very long, but some of it lasts for quite a bit of time. But our intuition is something like a third of all super rare variation, things that are at frequency 1 over 2n. A third of them are lost next generation. We clear? Makes sense? And we're up next with Julie for problem 7, it looks like.
Sure. Sorry, give me a second. Okay. Yeah, so for problem 7, if you pick up 2 alleles, the probability that they're identical is that you pick up 2 A1 alleles or 2 A2 alleles. So it's just P0 squared plus Q0 squared. And then probability that they're different by state can be either the first is A1, the second is A2, or the first is A2, the second is A1. So it's 2 P0 Q0.
That's all I'm looking for. In the current generation, the probability of two things being identical or different, let's bring in Hardy-Weinberg. The probability of two randomly picked things being the same, p squared plus q squared. Probability of two randomly picked things being different, 2pq. Thus, Hardy-Weinberg proportions are giving you the expected heterozygosity in the current generation and the expected homozygosity. In practice, there may be more or less heterozygotes. You might be in generalized Hardy-Weinberg. But in the current generation, the probability two randomly picked alleles are identical, Hardy-Weinberg. Two randomly picked alleles differ, Hardy-Weinberg. Or anything more complicated than that, that gives you Hardy-Weinberg proportions.
Dr. Cutler, I have a question about that.
Yeah.
So initially when I read this problem, I think I was just formulating in my head when you're randomly picking two alleles, I was assuming you pick one and you take it out and you can't pick it again. So you're sampling like
without replacement.
Yeah, so that's what I assume. But here we're just, you could pick the same allele twice.
Yep.
Okay.
So yes, I saw you picked without replacement.
Yeah.
If you pick without replacement, the formula becomes a little more complicated.
It did.
And in fact, it may actually end up looking like something like heterozygosity next generation or last generation. It's when you pick, it'll that is certainly it'll be a slightly more complicated formula. When you take a limit as 2n goes to infinity, it'll be exactly the same answer. But for the most part, we will always be picking with replacement because that's kind of how our model is going. Most of the time, we're thinking about some process where we're creating the new generation by picking two alleles at random from this generation, and we might very well have picked the same allele twice. And in fact, it'll be important to account for the fact that we might have picked the same allele twice. There'll be very few biological processes that prevent us from getting the same allele twice. You know what I mean? So yes, the words and phrases I'm using here may be somewhat ambiguous and not obviously well defined. But in the implicit assumption is almost always going to be picking with replacement, because that's generally how biology is doing it. That there isn't a good biologic mechanism that prevents picking with replacement.
Cool, thank you.
Yep. All right, I've already forgotten what problem we're on next. We're on problem 8, something like 8, with Mega. You with us?
Yes.
Yeah, I thought you were.
So I kind of just used the equation from, oh, it's not sharing. 1 second.
I kind of wanted you to just use the equation.
Yeah, I just used the equation from the book. I didn't know if you wanted it like simplified or anything. Is that not the right one?
It's probably not exactly the right equation. Well, it's getting there. It's probably H0, H sub t equals H sub 0 times 1 minus 1 over 2.
That's this one.
Yeah.
Yeah.
Yeah, the G is a little more complicated because we've got, is G is 1 minus H?
Yeah, I think I just flipped them, but I should have been writing like just H instead. And
Yeah.
I meant to write the like H naught times 1 minus 1 over 2n to the power of t.
Yeah. So that formula for 9 looks absolutely perfect. Though when we plug in 1 minus H naught for this term, and it'll get a little bit funkier looking probably. Does somebody else have this? Want to show it?
Are we on?
I can show mine if
Sure.
someone wants to. Oops. Okay, so just trying to derive the formula for expectation. Oops. Okay, so I guess you start with the definition of heterozygosity, and you go ahead and plug that into expectation. And if you multiply it out, you can distribute the expectation. And then you end up with expectation of P1 and expectation of P1 squared. Well, we know what this is, but we don't have the expectation of P1 squared. We do have the variance, so we can substitute for variance and just square the expectation of P1 that we already have. And if we substitute that in here, we can then factor out this guy, which is just the definition of heterozygosity. So we end up just multiplying by that factor each time.
Shit, I've never seen or thought about this way. This is exactly correct. I think this is just exactly correct. But I think this is getting out. This is an interesting way of thinking of this problem.
Oh, is this not like the standard way of doing it?
No, absolutely not. But this is exactly correct. This is absolutely reasoning from first principles. So the way the book would have, this is just exactly correct what you've done, but the way the book would have encouraged us to think of it is that there's this argument in the book that, so if H0 is the probability two randomly picked alleles are different from one another, the probability next generation that two randomly picked alleles are different from one another depends on two situations, two contingencies. With probability 1/2n, two randomly picked alleles this generation come from the same allele the previous generation. They are copies of the same allele from the previous generation with replacement. And with probability 1 minus 2n, they are not copies of the same allele with replacement. So H1 is the probability that these are not copies of the same allele the previous generation times the probability two randomly picked alleles are different, because those were two different randomly picked alleles, plus 1/2n times 0, which gives us H1 is equal to that, H2 is that, and you rather rapidly arrive at the conclusion HK is 1 minus 2n to the 2k H0 through nowhere near as sophisticated an argument as you just presented. Because you just said that HK is really a variance in allele frequency.
Can I ask a question about, because we're talking about how these are probabilities picking from that the alleles are different, but I think I didn't get that from the question, which was asking about them being identical by state. I interpreted that more as the homozygosity as opposed to the heterozygosity, so I didn't arrive at this answer.
So you understand why this answer is correct.
Mm-hmm.
And then for homozygosity, I just go 1 minus, bottom line. So for GK, that's equal to 1 minus HK, 1 minus HK, H0 is 1 minus G0. You see the line right before problem?
Yeah, now I see it. Actually, my
The screen was cut off, sorry.
my screen was cut off.
I'll move it up a little higher. So homozygosity, there is surely a similar argument to get us to homozygosity, but it's a little more convoluted sounding. It's much easier to simply say homozygosity is 1 minus heterozygosity and derive heterozygosity in this fashion. And then add some 1 minuses at the end, which is why you get something close to what Mega had, but there was a, I think what we had done is like we'd moved some 1 minuses. Anyway, it's a lot of 1 minuses. 1 minus 2n raised to the k, 1 minus g0. It's just plugging in definitions. But yes, this is a variance term, and you can derive it as a variance term. Okay. All right. All right, you want to go into something mundane like problem 9, Linnea?
All right, sounds good. Okay, so so number 9 involved programming, I think. I believe that's how we were supposed to do it.
That is exactly.
So basically, we already have the formula for heterozygosity from 8. So I think depending on how you like to program it, you could really do it any number of ways, but I just used a for loop, so I don't know if you want me to explain.
Every time.
Okay.
and you could even been more grotesque. And if you were really sort of like a Philistine, you could have done it in Excel, where you just have 1,000 columns, 1,000 rows or whatever, and just plug it in that way as a true Luddite. But that's it. It was nothing more than plugging values into a formula and plotting it, and what am I doing? Too stupid for this. The screen share, the thing to note though, the only thing we wanted to learn from this is that heterozygosity, even if it starts very, very high, will ultimately go to 0 if all that's going on is genetic drift. So genetic drift in the end will remove all the variation, that sooner or later only one allele will be present in the population if all that is going on is drift. Eventually 2pq shall be 0. And that's
I guess I'm getting a little lost, combining this idea with the previous thought you had about how the mean allele frequencies is not changing.
My God, you're right.
So
God, that's hard to wrap our heads around. So genetic drift all by itself is keeping the average frequency equal to a constant. But the realized allele frequency, or 2pq, is going to 0. So what does that have to mean? It has to mean some of the time p is going to frequency 1. Some of the time p is going to frequency 0 in such a way that the chance of it going to 1 times 1 plus the chance of it going to 0 times 0 is equal to the current frequency. That's the only way we can make sense of this. Because PQ is going to 0, but P is going to a constant. So on average. So it must be that P is settling in at a value of 0 or 1. But its chances of being 0 and its chances of being 1 balance out in such a way that its average hasn't changed at all. the only way that this basic math makes any sense. And it's at first blush a little hard to wrap one's head around that the variance goes to 0, but the allele, the expected frequency goes to a constant. That's because eventually the allele frequency must be 1 where there's no variance, or 2 or 0 where there's no variance. But the expected variance is going to 0, while the mean, the expected frequency is staying constant. Deep insight there. And that's how we're going, well, we'll see in a second. We'll see eventually. That's how we're going to drive some cute little results. But that's what genetic drift does. It keeps the mean constant, but it pushes around the allele frequency. The allele frequency starts out at something, and then it starts like, its distribution starts widening and widening and widening and widening and widening. And eventually, it ends up at frequency 1 or it ends up at frequency 0. That drift, any particular realization ends up at 1 or 0. The average ends up at P, and that's that. Questions? Okay, Taylor, you want to plot the next problem?
Sure. We're on number 10. Okay. Okay. So we kind of have this formula when there's mutation and drift. We have this formula for heterozygosity after 1 generation of random mating. But here we're assuming it's an infinite population. So I just let n go to infinity. So this term basically goes to 0, and we just have heterozygosity at the current generation left. And then I plugged in mutation rate u equal to 0.01 and initial heterozygosity of or current heterozygosity of 0.01. And this is the plot we get.
That will certainly work. You've probably, that 2u is probably something like 1 minus u squared or something that has become a 2u in approximation. But yes, I think 2u is exactly right. I'm not sure. Anyway, that's certainly right. And does this make sense? It's not quite labeled in her graph, but that number at the top is the number 1. So if we get rid of genetic drift, if there's no such thing as genetic drift, populations Taylor has also said in her head, the definition of no genetic drift is an infinite population size with no sampling. 2n is infinity. There is nothing there's no resampling at all. It's an infinite population effectively. But there is mutation every generation. And what happens to the probability 2 alleles are identical? It goes to 0. The probability 2 alleles are different goes to 1, if all you have is mutation. Eventually, everybody's got mutations. Oh, the underlying model here is an infinite allele model, where every mutation creates something that has never been seen before. So if mutation only creates new things, sooner or later, the entire population will have had a mutation and everything will be different from one another. Is this sensible to everybody?
If they do mutate to the same thing, if there's some probability it mutates to the same thing, would you just modify that equation with like a subtraction?
Yep, with like there'll be another term with a back mutation rate, and you'll end up you'll end up with it going to some sort of intermediate frequency that probably has is probably a function of the relative mutation rates. Other questions? So to give you the right idea, of course, why we think about the world having an infinite number of alleles. So, or an infinite number of well, either way, let's just talk about infinite alleles right now. So the idea we have in mind is we've got, like, I don't know, a protein of sorts. And we imagine that protein, there's a DNA sequence that gives rise to that protein. And that DNA sequence has, like, maybe 1,000 bases in it, maybe 2,000 bases in it. And every single nucleotide in there, a new mutation could be like one of 3 possible things. So when you make a mutation, there are like 1,000 possible places you could hit in the gene. And you have like 3 choices every time. So the number of possible sequences looks like 3 to the 1,000th power. 3 to the 1,000th power is like a lot bigger than the number of atoms in the universe. The vast majority of mutations shall never exist, have never existed, will never exist. Or rather, the vast majority of possible sequences. Just you're not going to get them. And so, although it is certainly possible you hit the same site twice, and maybe we'll do some math involving that, it is very, very uncommon. And for most of what we do, it will be uncommon enough that we just exclude that as a likely possibility. We approximate the system by assuming you never get it twice. Questions? All right, we are up next with problem 11, which looks like another sort of graphy thing with Brooke.
Sorry, did you say me?
Yep.
Okay, cool. I, rather than pull up my hand drawing, I will pull up my Excel that I,
Oh.
because my hand drawing is just a crude version of it. 1 second. Okay. So I actually put 11 and 12 together because I kind of thought they were interesting to look at together, but we'll focus on 11.
Very good idea, Brooke. All right, we're doing 11 and 12.
Okay.
So tell me about this. What am I seeing?
Yes. Yeah, 1 second. Okay. So what we are looking at, so 11 is asking specifically about the heterozygosity. So we have equations. We're looking at the heterozygosity when it's starting at 0.9. And so that's going to be focusing on the blue line, which sort of gets a little bit drowned out by the orange, but you can see that it's starting out at 0.9. So maybe I should have started with my drawing, but that basically is, we have our equation for heterozygosity, which is H0 1 over 2n. But we also need to incorporate a mutation. So that also includes a factor of plus 2 times the mutation rate times.
Let's click on the formula.
Oh, yeah. Well, so this formula, yeah, is kind of that. It's the, so what it's missing right now, or what it's done is it's the change in the time.
Mm-hmm.
So that's why it's turned into a negative term, because basically it's just this and this would be the kind of equation if you were to write it out on a piece of paper.
So this is exactly the same equation we saw a second ago. It's,
Yep.
it's that the change in H is equal to minus 1/2n times the current value of H. Genetic drift decreases heterozygosity at a rate of 1/2n, while mutation increases heterozygosity. It turns homozygotes, which is 1 minus B2, into heterozygotes at a rate of 2 mu. And that is the change. And then you found next generation from the chain.
Yep. And so then what you're seeing is that's approaching an asymptote at around 0.8. And then if you, I guess since it's basically the same thing for 12, but we're starting out with a different heterozygosity, which is 0.01, which is smaller. And then what that does is it has a big impact on the change because you're starting at an already small number. And so instead of this asymptote decreasing over time, you're actually seeing it increasing from 0.01 to about the same thing at 0.8.
That's it.
Yep.
So with both drift and mutation, heterozygosity, no matter where it starts, looks like it heads somewhere. It looks like it reaches an asymptote. And it does. And we'll talk about that in a second or two. But is this all clear to everybody? This is exactly what I wanted you to see in problems 11 and 12. That if you just iterate heterozygosity, leaving the sort of finding next generation as a function of this generation, repeat 1,000 generations, that if you start it very low, it eventually gets quite high, or at least it might. In this case, it does. It grows and grows and grows until it hits some value and then it stops. If you start it very high, it'll shrink. And by God, it seems to go to the same place twice. It seems to get there at about the same time, too, interestingly. That's that. Do we have any questions about that? So mutation and drift, if those are the only two processes going on, will eventually balance each other. And the population's heterozygosity will stabilize to a sort of fixed amount. Jim, do you want to do problem 13?
Sure. Okay, so kind of going off the last problem, well, using really the textbook, they gave us this nice equation to answer the question, what is the expected homozygosity at equilibrium? So here's the equation that the textbook gave us, but I didn't write it down, but they derived it basically from what we were doing above by setting the change to 0. And so for this problem, we just plug in, into the formula here, and you get 0.8, like what we saw in the graphs.
That is exactly right. Nothing going on here, but just plug in. So John, as a bit of an approximation, derives that heterozygous in this approximation, every single person on Earth uses all the time for the rest of your life. This is the value of H, really. But it differs very, very, very slightly. But this, so heterozygosity, the probability two randomly picked alleles are different from one another is equal to, at equilibrium, 4nu over 1 plus 4. From now, for the rest of my life, your life, I will say, if you hear me say the word theta, I meant 4n mu. That 4n mu will come up over and over and over and over and over again as we derive various quantities about mutual evolution in various ways. And the answer is always a pretty simple function of theta, usually. What is going to be the probability two randomly picked alleles are different? Theta over 1 plus theta. What's the probability of the same? 1 over 1 plus theta. That's going to be the answers. And we're going to get to even fancier probabilities. What is the probability two randomly picked sequences differ by exactly k alleles? It'll be a relatively simple function of theta. What is the expected? It'll be a theta. What is the variance? It'll be a function of theta. You will see 4NU repeated in almost everything you do when all that's going on is mutation and drift. And the reason, the intuition you should have is the reason it's 4NU is 2N is the number of alleles and 2mu is the number of mutations, effectively. So for almost everything we do, there's going to be like 2 mutations possible, giving us a 2mu, and there are going to be 2N alleles, giving us a 2N, and our 2 mutation thing and our 2N thing are going to combine in a way to make it 4NU. And when we do the next homework, and maybe one after that, you should really be thinking, I bet the answer looks like 4NU in some fashion. You know, maybe a little complicated, you know, maybe the theta don't want to, it might get a little uglier than that. But by God, you're going to be surprised by the end of this if the answer isn't a relatively straightforward function of 4NU. Over and over and over again.
This might be a little bit of a distraction, but when I was doing all this stuff on genetic drift, I was thinking about the concept of gene drives. And CRISPR-enabled gene drives, which basically change an allele even when it's in a recessive state to become the only allele. Is there a way to change this kind of formula to something that encompasses that, or have people done that?
Yep, and very much. And we're going to the word you're going to be looking for that is natural selection. Only in this case, artificial selection. But you're going to think about the change in allele frequency if you were trying to build one of these, these drive-y type systems. You're going to think about it as in the exact same way we would think about nature doing it. Only if you're doing it, you're nature. But the mathematics for it is going to be exactly the same as if it were happening naturally, rather than by your little poking. And the way we will derive selection is the exact same way we derive drift. We will start with binomial sampling, but the probability of sampling an allele will not be its frequency. It'll be some more complicated function. And so next generation, the expected value of A1 will not be its current value. It'll be something else because selection has made it more likely or less likely we pick the A1 or the A2 allele. And we will probably end up writing down the probabilities of sampling as, say, some function of genotype. And then we will think about the way natural selection or maybe the way you do selection in the lab could affect the probability of a genotype giving rise to the next generation. Does that make sense to you?
Yeah.
We will get there, I promise you. And if you leave this course without being able to think about a artificial selection experiment and not having a good way to estimate how the allele frequencies ought to change from one generation to another, I have failed you. And you should say, Cutler, we fucked it up. We got it. Like I should be able to do this. And we're going to try to get there. Any other questions? All right, Mitchell, you want to take the next problem?
Sure. Which one is that? 14?
I think it's 14.
Okay.
Ooh, yeah, this one's yeah, I like this one. Cool.
Doesn't sound
That's-
good because I didn't have that reaction when I did it.
Well, you may not have the same love of this that I do. May not be any inherent love in part of this.
So I just thought it was plugging it into that same equation, but now 14 reads that you have 12,500 diploid individuals, and then it gives the starting heterozygosity. And then I wanted you to estimate the mutation rate. So I just solved for the mutation rate using that equation and then plugged in H and N for these values. Not sure if that's correct.
So, so what I give you? I gave you the starting heterozygosity, and yeah, and let me see what I was just looking at my notes to see what values we ought to be getting, and so show me what you had there. You got, yep, that looks like the value I have too. But, does anybody else have a different value? You got something like 2.2 times 10 to the minus 6 if we've all done the arithmetic. It was really just arithmetic, maybe a little algebra. If we've
So
done
oh, sorry. I think I keep making the same mistake, and so I just kind of want to clarify it because it's a little unclear in Gillespie. There are two different approximations, I guess, that are put into Gillespie for H hat, and one's the 4NU over 1 plus 4NU, and then I think it also says that that can be also seen as 1 over 1 plus 4NU, but they're very different values, and I've noticed that I've been making that mistake.
G H G H.
It's
G.
oh, okay, that's what's going on.
Homozygosity is 1 over 1 plus 4NU.
Okay, thank you very much. That's an easy mistake. Thank you.
And there's a good way for you to think of it. So imagine that mutation is really, really, really big relative to, or just imagine that, or rather, let's put it the other way. Let's imagine that, well, just think about 4NU at it. So if 4NU is a big number, that says there are a lot of mutations every generation. You think of mu as like the probability of a mutation per generation per person. If 4NU is a big number, that says there are lots of mutations every generation. So at equilibrium, the probability two alleles are different from one another looks like 4NU, the number of mutations, over 1 plus 4NU. So more mutations will equal more heterozygosity. On the other hand, if 4NU is a little bitty number, 4NU over 1 plus 4NU is a tiny number, and heterozygosity will be little. But 1 over 1 plus 4NU will be a number like 1, which means homozygosity will be big. So a little theta leads to mostly everybody being homozygous, and a big theta leads to mostly everybody being heterozygous. And that's why one of them is 1 over 1 plus theta, and the other is theta over 1 plus theta. The most confusing bit of all is if you're talking about a per site thing. The heterozygosity per site theta will be a small number. So Gillespie and other adults, when they write down heterozygosity is equal to theta over 1 plus theta, will sometimes immediately approximate that as just theta by getting rid of the 1 plus a little number on the bottom. And that will occasionally be a bit confusing next week. That whether heterozygosity is best approximated by theta or the heterozygosity is best approximated by theta over 1 plus theta. But the way we've derived it, it's 4NU theta over 1 plus 4NU. Is this sensible to everybody? More total mutation, more heterozygosity, less total mutation, more homozygosity. Homozygosity is therefore 1 over 1 plus it, and the other is, and obviously that homozygosity equals 1 minus heterozygosity, and vice versa. In case that isn't completely obvious. And I think that's probably a good place to stop for today. We've gotten through the vast majority of the problems. Next week, we'll start with a new list and finish off the problems. And then if you look at homework 4 before Thursday, come with your questions. Homework 4 will be an extension of this. We will reapproach some of these results in what is sometimes referred to as a coalescent framework. You will, if you read the book, learn what the word coalescent means and learn how, using sort of coalescent tricks, we can get many of the same results. In fact, we can get full distributions for some things a little bit easier than we might have in this framework. And by the end of next week, you guys should have really a good understanding of what neutral evolution is, what you expect out of it, and how you can use, if you assume the world is neutral, how you can use sequence data to estimate most of these parameters. We can, if you give me the sequence of a bunch of individuals, I can tell you what theta is in my head most of the time, roughly, because it's sort of very simple formulas in the end. Count it on your fingers. So the use of next time for those of you who are going to be involved in molecular evolution is in part so that you always, always, always have in your mind what the neutral expectations are, so that if you see something radically different than that, it means you're either about to get famous or you screwed up your experiment. One or the other is true, and it's much more common that you've done something wrong. Vastly more common. But you will see that most sequencing experiments give you results that are not inconsistent or not deeply inconsistent with nothing more than neutral binomial sampling most of the time. Not always, obviously, but that'll be the sort of baseline null model that you'll be rejecting the rest of your career in some fashion or another. Other questions? Okay, guys, we will finish the homework next week. Come with questions about homework 4. It is much like this. It is challenging and it is long. But many of them are like this also. Plot, nothing fancy. Cool. See you Thursday.